So let's get started. So as you all know, deep learning has made very important progress, especially lately. There's a lot of excitement around it. And so there's a lot of applications where there's been a lot of important progress with scaling up deep learning. But there's still a lot of limitations of deep models. So in particular, deep models often rely on large training sets to learn a particular task. And then once they've been trained, they're not always adaptable easily to solve new tasks. And this is in stark contrast with how humans learn. So humans can learn flexibly, and we can even learn from a single example. So even if you've never seen that object in the red rectangle before, which I actually learned from reading Brendan Lake's paper that that's a segue, even if you see just one of these, you can probably recognize others when you see them, and even from a single example, you can start to recognize segues from now on. So few-shots learning and meta-learning are two research areas that are trying to bridge this gap between how flexibly humans can learn and how deep learning methods learn. So I'll define these two terms and their relationship here. So few-shot learning is the study of learning new concepts from few examples. For example, new object classes, like the segue. And the way that we expect this to be possible to learn new things quickly is by leveraging knowledge obtained from previously seen concepts. Like maybe you've never seen a segue before, but you've seen a bicycle, so there's some transfer there. Meta-learning is about learning how to learn. So the hope here is that we can expedite learning new tasks because we've seen other tasks in the past. And there's two ways to think of the relationship between these two. One way is to think of few-shots learning as a useful evaluation protocol for meta-learning approaches. And the other way is to think of meta-learning as a useful approach, a useful methodology for achieving few-shots learning. And this is going to be the viewpoint that I'm going to take in this talk, and I'll expand on what I mean with this throughout the talk. So this field of few-shots learning and meta-learning has evolved very rapidly over the past decade or so. It started off with using very simple data sets like Omniglot, which has like handwritten digits on a very plain, easy black background, all the way to larger and more complex data sets. And the architectures also evolved from using very small convolutional networks to very large ones nowadays. And the approaches evolved as well. So I'll kind of follow this roadmap throughout the talk. I also gave a NeurIPS tutorial on this topic where I go into more depth in each of these kind of eras, and I won't have time to go here in full detail, and so I'll spend more time on the later part of the roadmap. So let's begin with this early days, this era that I'll call the golden age of metric learning and meta-learning, where folks were pretty convinced that to get a good few-shots learning approach, meta-learning and metric learning were important ingredients. And I'll define all these terms now more concretely. So few-shot classification is the flavor of few-shots learning that we'll focus on here. So what this means is the following. We have a large training data set available, shown here on the left. And the goal is to use that training data set in order to come up with a model that can so-called few-shots learn new classes. So how we're going to measure and do that is by asking it to solve many of these so-called few-shot learning tasks. So each of these boxes here on the right is a task, and each few-shots learning task contains new classes. So here, this vase thing, dog and spider. These no vases, dogs, and spiders were in the training data. From that perspective, it's few-shots learning. So these are three new classes. And so these are the three new classes that this particular task introduces. And the task comes with a support set, which is a small training set for that task that contains a few shots. In this case, this is a one-shot task because there's exactly one training example per new class introduced. And it also has a query set of other examples of the same three classes that are not labeled. So the goal of the few-shots learning model is how can you use these few labeled support set training examples in order to understand these new classes well enough to classify the query examples correctly. So in order to approach this particular problem, one must face two challenges. The first one is the upstream challenge, which is how do you go from this large training set to a model that has this few-shot learning capability? And the second one is the downstream challenge, which is that given that you have this model, what's your approach for using it to digest these small training examples in order to teach the model that new task? And meta-learning is a particular approach to the problem, or can be seen as such. And as such, it has a particular response to the upstream and to the downstream challenges. And I'll tell you a little bit more about how that is done. So the idea in meta-learning is that you have that training data set available, and you're just going to make the design choice to say that, you know what, I'm going to use this training data to sample many so-called training tasks. So these are tasks from the structural perspective. They have a support set and they have a query set, just like the tasks that you want to solve at test time. But of course, the examples that populated just come from the training data now. So you have the labels for them because they're part of your labeled training data set, but you're pretending that you don't for the query set in order to construct things of this structure. And then once you have these, the way that the meta-learning update works is as follows. Let's say that we have a feature extractor. So our neural network classifier can be comprised of a feature extractor followed by a classification layer on top or something. And we're going to assume here that we want to meta-learn the feature extractor parameters. So the way in which we would do this is to sample a training task, one of these things that we constructed that has a support and query set. We'll use the support set to do some task adaptation process. I'm being vague because that depends on your choice of meta-learning model. But in general, you're going to do some task adaptation process to make your general model be a task-specific one. And your task-specific one is going to contain a classifier for whichever classes appear in this particular task. And it may or may not also update the feature extractor to make it appropriate for this particular task. And then you're going to use that to make predictions for your query examples. So mathematically, for a query example, that scared me. For a query example, x star, you're going to make a prediction for its label y star conditioned on the support set. Conditioned on the support set because you use the support set to come up with the task-adapted model, right? So you're adapting on the support set, then using that model to make query set predictions, and then it's that loss that goes and updates your meta parameters, which here are the feature extractor. So why is this important? The insight here is that you're training your meta parameters specifically to be good on a query set after having conditioned on the associated support set, which is exactly the type of thing that you have to do at test time. So you are training your model specifically in preparation for the thing you want it to do at test time when you're doing meta learning. And this was advocated to be really helpful. Metric learning I won't go into in detail because of time constraints, but generally it's the idea that you want to learn your feature extractor such that it, the feature extractor, just to be clear, takes images or whatever your inputs are and outputs some vectors that represent them. And you want to train your feature extractor in metric learning such that if you embed similar inputs, the outputs will also lie close by, and so on. And this is useful for few shots learning because the hope is that if you get new classes, you can still get reliable similarity estimates between examples, even of new classes, and then you'll be able to judge, you'll be able to make predictions for query sets. So without going into the details of that, I'll give you some examples of metric learning-based meta-learning. So the only thing that changes compared to what I've told you here before is that when you do the task adaptation process on the support set, you don't change the feature extractor. That is kept fixed. So to adapt your general model to the particular task at hand, all you do is you figure out how to make classification decisions for your query examples using some similarity estimate between the query example and members of the support set. And so this could be like cosine similarity. There's many choices for how to do. You have similarity between a particular query example and a whole set. So there are some design decisions for how to do that. And in particular, prototypical networks are a popular option. And what they do is that you have your support set shown here. The different colors belong to the different classes. So what prototypical networks do is they just embed all the support sets with the feature extractor and compute one prototype per class, C1, C2, and C3, by just averaging the embeddings of the support examples that belong to that class. And then to predict the label for a query example, you just embed it as well, and you say in this particular case, oh, it's closer to the prototype for class 2, so I'm going to predict it belongs to class 2. And I'll briefly also introduce MAML, which is another flavor of meta-learning. This is optimization-based meta-learning. And so how this works is that during task adaptation, the adaptation algorithm in this case is a few steps of gradient descent on both the feature extractor and the classifier, and that's how you get your task-adapted model. So what does this mean? So intuitively, right, you have this general model that's updated throughout tasks, and every time that it sees a new task, it's going to do a few steps of gradient descent on the support set of that task, then make query set predictions using that task-adapted model, and then go back and revise the meta parameters, which were the initialization, such that this works better next time. So intuitively, you can think of this as you're meta-learning this parameter vector theta such that one step of gradient descent in the direction, each of these are different tasks, imagine, you want to learn theta such that a single step of gradient descent, or just a few, suffice to turn theta into these theta star counterparts, which are the best parameters for the corresponding tasks. So MAML tries to meta-learn a good initialization. How do these things compare empirically to each other? At the time when some of these methods started emerging, there were some simple data sets that folks were using, like Omniglot, which I already mentioned, has simple visual concepts. And Mini ImageNet is a subset of ImageNet, so it's a bit more diverse, as you can see, compared to Omniglot. But still, it's quite simple. If you squint a little bit, all of these look like the same classes. There's not a very large semantics gap between training data and the new classes appearing in test tasks. And at the time, without going into the details here, these are a bunch of methods. I haven't talked about all of them, blah, blah, blah. But some takeaways are that models like prototypical networks, and this one that we proposed in this paper, which you can read another day, are performing strongly, stronger than MAML usually. But one of the important things to point out here is that this is a time when folks were using, yes, I think I can share the slides after the presentation. So at this time, folks were using a simple convolutional network of just 4 convolutional blocks, which is quite small. So we'll start seeing how this might have affected the conclusions for what sorts of methods work very well. There came this era where people started questioning the necessity of meta-learning. So we started seeing papers with titles like A Baseline for Few-Shot Image Classification, A Closer Look at Few-Shot Classification, Rethinking Few-Shot Classification, and so on. And of course, each of those papers proposed a different method, but there was a common thread, a shared methodology in all of these, which is what is sometimes referred to as a transfer learning baseline. Baseline in many, many quotes, because this is a strong model. Maybe we shouldn't be thinking of it as a baseline necessarily. But the idea is, standard supervised learning. You take your training data set, sample mini batches, not support query task things. You just sample mini batches, images with their corresponding labels, and you go and train a global classifier. Global in the sense that it has labels for everything in your training data set. Standard supervised learning. And then, of course, at test time, we're seeing new classes, so this classifier layer is not useful, but we can reuse this feature extractor to get good features for test classes as well. This is the thought there. So how would you actually solve few-shot learning tasks with that, right? So at test time, you have a support query set kind of structure, few-shot learning task. You use your feature extractor that you got from the big training phase that just passed, and you can just learn a new classifier on it, on the support set, and then just use that to make predictions on the query set. You can even fine-tune the feature extractor here when you're training the new classifier, but commonly in these baseline papers at this time, they were not doing this. So empirically, how does this compare? Again, big table, lots of numbers, don't worry. But I want to draw your attention to 2 points. The backbone column, you see these like early 64 filters per layer. There's just 4 layers, convolutional blocks, and then people started using ResNets and even wide ResNets. So the backbones are evolving to become deeper. I'm emphasizing this for a reason. I'll come back to this in a second. The other thing is the last two rows are taken from this paper, Rethinking Few-Shot Image Classification, which belongs to this transfer learning methodology. I haven't told you what the difference between simple and distill is. Simple is more like what I showed in the previous slide, and distill does many rounds of the upstream global classifier training, where you would train a new student at every round to predict the soft labels from the teacher, rather than predicting one hot labels. If that didn't make sense, don't worry about it. But the main takeaway here is that each one of these follow the very simple recipe of adapting to a new task, which is, I already have a feature extractor that was learned without meta-learning, just standard supervised training. I have that feature extractor. I'm just going to learn a new classifier on top. No even adaptation of the feature extractor. So this is conceptually simple compared to, you'll have to take my word for it. Some of these are more complicated, and a lot of them involved meta-learning. So this methodology is much simpler, and it works much better than some of the other things. So what's going on here, right? Like, I kept talking about backbones, so you can take my word for it that these backbones, these ResNets, have more parameters than the simple convolutional networks. And this is important for making the transfer learning baseline work. If you don't have enough parameters in your network, then this simple recipe of train a global model and then just learn a new classifier on top is not going to work really well, because you need more parameters to be able to have that feature extractor discover good features. So we were perhaps biased by looking at those smaller architectures. We were biased against that solution. But still, you might be surprised, why is this working so well? So one hypothesis is that the data sets that we're using are too simple. I already talked about Omniglot and Mini ImageNet. Tiered ImageNet is another variant that we proposed in a paper that I'm linking there. My colleague Jake Snell in particular worked a lot on this, and the idea is that it's another subset of ImageNet, but we divided things into meta-training and meta-test classes in such a way that there's greater separation semantically between them. And so we thought we were creating a harder task. But still, you can say that the training classes and test classes still look alike in all of these cases, so that it's maybe believable that you can reuse a feature extractor and not adapt it too much. So there might be a common set of features that you can just learn from the training classes that also happens to discriminate between the test classes. And in that case, you're good to go. Perhaps you don't need adaptation of the feature extractor. And there's tons of evidence in at least 2 or 3 papers at the time that this might be what's going on. So to address this, we proposed a metadata set, which is a much more diverse and complex environment for studying few-shots learning. So this is a data set of 10 publicly accessible data sets, as you can see here. So we hold out these two, traffic signs and MS COCO, we hold them out for evaluation. That means you're not allowed to train on any examples of any classes of these. Yeah, maybe an arbitrary choice, right? But I'll go into that a bit later. And for each of the other 8 data sets, we split them at the class level, so that some of their classes can be used for training, and some other classes are held out for creating few-shot learning tasks. So what does few-shot learning look like here? Same story at a high level, right? You have this training data set. How do you use it to create a generalizable model that can then few-shots learn? But now this training data set is very heterogeneous because it contains classes from each of the 8 first data sets. And then the goal is to use your model that you got from the training phase to solve each of these few-shot learning tasks. And I'll make a distinction here between tasks that I'll call weak generalization ones and strong generalization. So weak generalization, like this flowers one at the top, are tasks that, all of them are few-shot learning tasks. So the classes are new, but the classes in the flowers task come from a data set from which other classes were seen at training time. So even though these classes are new, there were other flowers at training time. And so there exists at least some part of the training data set that was quite relevant for solving this task. Whereas strong generalization tasks come from held out data sets altogether. So it's new classes, but also from new data sets. So they look less similar to the training set. And then following recent work, we added 3 additional held out data sets, CFAR10, CFAR100, and MNIST, just to have more of these strong generalization tasks available to us. Cool, so I just picked some tidbits of the initial investigation we did into metadata sets, which I think are still relevant today. So I'll tell you about just these parts of this paper and then move on. But so the questions that we wanted to answer are the following. Is adaptation of the feature extractor useful on metadata sets? We saw previously a couple slides ago on some of the simpler data sets that you don't really need to do this. Do you need to do this now? How well do different methods exploit diverse data? So now our training set is heterogeneous. How can we, this adds new challenges in terms of digesting all of that diverse data. And is meta-learning useful? Do we need to do it to get a good few-shot learning algorithm? So we tried some of these transfer learning baseline methods here too, which is the same recipe as before, except here the classification layer on top is the concatenation of classifier for ImageNet, Omniglot, blah, 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 each of the 8 first data sets that have some training classes in them. And we train a feature extractor like that. This is the simple, standard supervised learning recipe, again, for this baseline. And at evaluation time, we tried 2 variants. One actually fine-tunes the feature extractor using the support set of the particular few-shot learning tasks that it has to solve at test time. And the other one doesn't fine-tune it and does instead some simple metric learning thing on top. We did like a one nearest neighbor approach. And then we tried a bunch of meta-learning models as well. We noticed that prototypical networks, which I showed you before, does really well, even though it's really simple. But we hypothesized here that we probably need to update the feature extractor as well, which prototypical networks does not do. It just, to remind you, has a frozen feature extractor and uses the support set only to compute prototypes by averaging support examples of each class, and then makes predictions for the query set by distance to the prototypes. So we hypothesized that we need to adapt the feature extractor too because of the higher diversity here. So we proposed a variant that combines prototypical networks with MAML, which adapts the feature extractor with gradient descent. And in a moment of great creativity, we named this proto-MAML. So I'll show you now what this does. It takes the support set and uses it first to compute prototypes, just like prototypical networks do. And then it uses that to initialize the classifier layer. So now we have the initialization from the feature extractor that we inherited from the previous update, the initialization to the classifier, and we go and now do a few steps of gradient descent. So this is the MAML bit of it, to get the adapted model and then make query predictions and then go and update the meta parameters, which in this case is just the feature extractor. So this is exactly the same as MAML. The only difference is the initialization of this classifier for the task, which is done in terms of the prototypes computed from the support set. And we see here, by comparing performance on metadata set, that proto-MAML does better than prototypical networks. This means that adaptation does matter because prototypical networks is like proto-MAML with 0 steps of adaptation. And we also see out of the 2 baseline methods that the one that fine-tunes the feature extractor is better than the one that doesn't, which again hints at the same conclusion. Now, how well do methods exploit diverse data? In this funky visualization here, the best performance is the one that is closer to the outer circle. And this is the test performance on tasks from each of the 10 data sets, the test accuracy, I should say. And so purple line is when you use all of the training data available to you. And the dashed blue line is when you ignore all data sets except for ImageNet and use only ImageNet. So the dashed blue line is using much less data. But ImageNet is, in general, if you haven't heard of it, a data set which is hypothesized to be a good source for transfer. So if you're to pick one, let's pick that one. And you can see that the one that trains on all does much better on these 3 cases, aircraft, quickdraw, and Omniglot, which is expected because these ones look very unlike ImageNet. And the purple line includes some classes from them too in its training. So this is very expected. But the surprising bit is that how come purple doesn't do better everywhere? It uses a lot more data, and surely there could be some transfer between all of these data sets. And so we were surprised by this. And by the way, this isn't specific to prototypical networks. We ran the same experiments on other sorts of meta-learning methods, and this seems to be kind of common across the board. And a bit later, I'll show you a newer method that we developed that does a better job at exploiting diverse data. Okay, and how helpful is meta-learning? We really wanted to study this in a controlled way to understand what's going on. So we proposed a set of what I'll call inference-only baselines. So I'll say what this means by explaining with an example with what's an inference-only prototypical network. So this is a model that at training time acts like the baseline, so standard supervised learning. But then at test time, it acts like a prototypical network. So it uses the support set to compute prototypes, blah, blah, blah. So an inference-only prototypical network uses the inference algorithm, that is, how do you use the support set to adapt the model to classify the query set? It uses the inference algorithm of prototypical networks, but it trains a feature extractor normally, not with the prototypical network's recipe. Whereas, again, to contrast this, the usual thing to do is that you would prototypical networks is a meta-learning model, so it would train the feature extractor on many training tasks, on each of which it would apply its inference algorithm. So here we're disentangling, like, are prototypical networks good just because they happen to have a good way of solving tasks at test time, or also because they meta-learned to prepare specifically for applying that recipe? And we see here, we compare the inference-only version of prototypical networks is in purple, and the dashed blue line is the meta-learned one. And we see that meta-learning does not help significantly, actually, here. Sometimes it even hurts. This is trained on all of metadata sets training data. But we notice that if you do this only on ImageNet, if you do the meta-learning phase, the initial training phase, only on ImageNet, then you get a more clear win from meta-learning compared to inference only. So this also hints that maybe there's something challenging about meta-learning on heterogeneous tasks. Maybe we just need to study better how to do that. And when you do it only on ImageNet, there's a bit of a clearer win. And again, we draw the same conclusions for other meta-learning algorithms, like matching networks, which I didn't tell you about today, and the proto-mammal one as well. Okay, so I'll move on to talk about a bit more recent work now. Since we did this initial investigation on metadata sets, sorry, the font is a bit small, but on the x-axis you have methods that were developed since. So the point all the way in the left is the proto-mammal model, which is the one we found worked best in our initial investigation. And since then, you see many other models that are created. And this curve is the accuracy averaged over all tasks on metadata set throughout the years. This is late 2021 on the right. And actually, several of these approaches are hybrid models that do some transfer learning and some meta-learning. So for instance, some of these here on the left, like the Synapse model from folks in Cambridge, is meta-learning networks that predict task-specific layers to interleave into an otherwise pre-trained and now frozen feature extractor. So there's the transfer learning baseline kind of thing going on to train that feature extractor. And then there's a meta-learner that tries to insert task-specific layers in order to adapt that general feature extractor to the task at hand. So that's a particular hybrid approach. Oops. Yeah, and some of these other ones are also hybrid ones, and I'll tell you about them next. So this brings me to this part of the roadmap where folks started combining pre-trained components with meta-learned components. And I'll begin by talking about universal representations, which refers to a rich set of features that enable strong performance on various data sets. This comes from a computer vision, an older paper from Billin and Vidaldi. And the idea was adapted to work on metadata set as follows. You have these 8 data sets that you're allowed to train on. Go off and train a separate feature extractor on each of them. Or instead of being entirely separate, they can maybe share some weight. So maybe you train the ImageNet one first, and then you copy a big part of the weights over, and you allow to specialize some others. But we can just think of them for now as you have one feature extractor per training data set. And then to solve any new few-shot learning task, the idea is that you obtain this universal representation first, which is the concatenation of features from each of these 8 things, forward pass concatenate. And then you can think of different approaches for selecting relevant features from this. So the idea is this universal representation contains a bit of everything, and you select relevant features to solve the tasks that you care about. So one approach to doing this is SIR, which stands for Selecting from a Universal Representation. And the way that it does this is it has an iterative optimization using the support set where it produces these lambda coefficients, and these weigh the different components of the, so there's as many of these as there were training data sets, so in this case 8 on metadata set. And these lambdas weigh these components of the universal representation in a way that's good for this particular task. And then you use that as your representation, and you can do something simple like compute prototypes in that space and use that to classify query examples or some other rule based on these representations. URT stands for Universal Representation Transformer and is a different way of doing this, where here they say, okay, I have all these feature extractors, one per training data set, and I'll keep them frozen, but I'm interested in meta-learning a transformer layer, so an attention layer, that takes in the support set of the task I care about and uses that to determine how am I going to blend all the things I have available to me to create this task-specific representation that works well for this particular task. So the support set here, you can aggregate it, you can average it to get one representation. This is the query in the attention sense, and these are the different keys in the sense of the attention mechanism. If you're not sure what the attention mechanism, the transformer layer is, don't worry about it. But it uses the support set to search for good ways of combining the existing things that you have. And so this is a meta-learning phase where you keep the feature extractors frozen and you meta-learn the parameters of that attention mechanism. And here meta-learning is useful for two reasons. This transformer layer, once it's meta-learned, you can think of it as having discovered a better combination strategy for the available features you have from the pre-trained backbones, rather than picking a heuristic one. Because you are training it specifically to combine things such that the result works well on the query set each time. And the other benefit is amortization. Remember in SIR I showed you there was an iterative optimization to produce the lambdas each time. Here you don't need to do that. You do your meta training phase, you learn that transformer layer, and then at test time you just need to forward pass through it in order to get the task-specific representation. So meta-learning can give you amortization, and it can discover a better strategy for doing something rather than picking a heuristic. And we see empirically that URT, this meta-learn transformer thing, works better than SIR, which is a more heuristic one, on average, but it works better primarily in terms of weak generalization tasks, not strong. So remember, weak are the ones that are new classes, but from data sets that you've seen in the past. So these are easier to generalize to. So we then proposed a new method that, in particular, we tried to improve the strong generalization. And so for this, we are putting forth a different inductive bias. Instead of trying to learn a diverse feature vector, as it's done in universal representations, we instead want to learn a template that can produce diverse feature extractors that differ in several levels of the representation. Because we hypothesize that to generalize to a very different task, it doesn't suffice to pick from high-level features, because those high-level features won't be very relevant. This is the premise of strong generalization. So instead, we want to modify the feature extractor in a deeper way. So we refer to this inductive bias as few shots learning with a universal template or flute. And what we mean here by a template is a partial feature extractor. So these blocks that you see called universal template are the ones that will be shared across all tasks. So this little diagram here is showing you the feature extractor for a particular task. And it's a partial feature extractor in the sense that you need to fill in the blanks to make it a complete feature extractor that works well on a task. So maybe these green values for a blank give us a good feature extractor for ImageNet, whereas these pink ones for flowers, and so on. And we propose a way to learn those blocks such that they can act like a universal template. So we do a joint training phase over all of the available training data sets. Again, these are 8 on metadata set, where here you're seeing the feature extractors for all of them. They have a different classifier layer for each one because different data sets have different classes. And other than that, the feature extractors are allowed to differ in terms of their film parameters. So film stands for feature-wise linear modulation, and there's a nice Distill article here from Vincent Dumoulin on the topic. But essentially, you can think of this, it's in fact commonly implemented as different batch normalization layers. So if you're familiar with the batch normalization layer, it's a common layer in many architectures, and it does some normalization followed by an affine transformation channel-wise. So you have a multiplication by a gamma and an addition by a beta. And what these colors mean is that if you come from ImageNet, oh, let me grab you the green gammas and betas. If you come from whatever this was, Omniglot, let me grab you the blue gammas and betas. But otherwise, all the parameters are shared. And so crucially, what we hypothesize here is because the different feature extractors differ only in their film parameters, batch normalization parameters, which are very small number compared to the overall parameters, what we are hypothesizing here is that the convolutional layers are forced to do the heavy lifting in terms of this producing feature extractors that work across tasks. So the convolutional layers need to do the heavy lifting in terms of generality, and thus they are forced to turn into a universal template, at least when it comes to the 8 data sets that we are using here. And so then to solve a new test task, how would you use this? Well, the premise is, of course, we're going to reuse the universal template, but you need to fill in the blanks. So you need to find gammas and betas, the batch norm parameters for every block in the network. And we propose to learn those with gradient descent. But we notice that the initialization of those parameters really matters. So we propose a way to tailor it to the task at hand. So given a new task, which again has a support set and a query set, we would feed the support set in a set encoder. This just summarizes it. It's some neural network that takes all the support images and outputs one vector that's the summary of the support set. And then we feed that into a dataset classifier. So we train the set encoder and dataset classifier separately in a different phase to just take in support sets or take in sets of examples and tell us which dataset of the 8 available ones it thinks that they came from. And so once we have that, we can, this will give us a vector of probabilities with which it thinks that this particular support set, and so this particular task, came from each of the M training data sets. And we use these to take a convex combination of the available film parameters that we have for each of the training data sets. So what's the intuition here? If the dataset classifier looks at this task and says, oh, hey, I think this comes from QuickDraw, then the probability for QuickDraw, whichever that is, that pi, where I is the QuickDraw one, would be very high. And so you'll be effectively primarily choosing the film parameters that you learned specifically for that data set. But we make this soft because, well, this is a hypothesis, but new data sets might not look particularly like any given training data set, and we hypothesize that this combination would be useful. In practice, by the way, we found that a hard selection also works really well, but this seems more general. So anyhow, so we do this anytime that there's a blank that we need to fill, so anytime that there's a batch norm parameters that we need to set. We combine the batch norm parameters of the individual training sets according to these probabilities from the dataset classifier. This is just a heuristic. We were proposing this as like, oh, hey, here's a simple thing that you can do that works well. But there's room for improvement here, maybe meta-learning opportunities. Can you meta-learn how to combine those film parameters such that they work well given a new task? So you can imagine some kind of transformer layer again. You can go wild here. We found here, importantly, that the flute model, so this approach that I'm just talking about now that constructs a universal template from diverse data sets, works much better than using only the gray bar, which is using only ImageNet. So we're comparing here, what if we, instead of using all these diverse data sets to come up with a template, we train the convolutional blocks, so the universal template blocks, only on ImageNet? That massively underperforms. So the two groups are for weak generalization and strong generalization. It massively underperforms across the board, which is contrary to what I showed you a few slides ago, where the initial meta-learning methods that we were looking at did a poor job at exploiting more data. So if you use just ImageNet versus all data sets, you would get something similar there. And now perhaps we have methods that are better equipped at leveraging heterogeneous data sets. I'll briefly mention this approach as well, which is concurrent work to Flute, and also can be seen as using a template, though I would argue not learning a template, but using one. So they go and pre-train these parameters on ImageNet, I think, and then they have a more sophisticated way here of filling in the blanks of the template, so coming up with film parameters, where just very briefly, they have two branches. So you take the support set as input, and then the top branch makes a hard selection, again using a dataset classifier, says, oh, I think this support set, so this task looks like Omniglot, so I'll pick only the, I think green was ImageNet, only the ImageNet parameters. And the bottom branch does a soft combination using some attention again, and then you fuse these two to come up with the final parameters. I'll leave you to look at their paper for more details, unless there's any questions. So this actually uses some meta-learning, and again, the benefits can be seen as twofold. This has the potential to discover a better combination strategy of film parameters compared to, for instance, the simple heuristic in Flute. And amortization. Once you train this, all you need to do to solve a new test task is forward passes. You don't need to do any gradient descent. Whereas in Flute, we had this blender heuristic for the initialization, but then we went off and did a few steps of gradient descent from there. So how do all these things perform? The big takeaway here, so orange line is strong generalization, green line is weak generalization. The big conclusion here is that the templates, both Tri-M, the one I just talked about, and Flute, work much better than universal representations for strong generalization, and this comes sometimes at a small cost in terms of weak generalization. And I think this is expected, you know, there's different inductive biases there, and again, combining high-level features, which is what universal representations do, might be appropriate for weak but not strong generalization. A particular disadvantage of Flute is that it requires that special joint training phase to learn the template, which is, I say that this is a disadvantage because a nice thing to do these days is grab off-the-shelf models and figure out how to combine them after the fact rather than having to train a model in a special way. So I'll briefly mention universal representation learning, which is work that came after that mitigates this issue. So here they train one feature extractor per dataset, or they can grab their favorite feature extractors, and then they have a distillation phase to distill all of those into what I'll refer to as a universal feature extractor. And now they can do some simple adaptation at test time on top of that. Follow-up work from the same team actually studied more sophisticated adaptations using these things called residual adapters, which are like the film layers that I talked about before, but with some more capacity. And I'll just say quickly that you can get massive improvements from these URL variants, but if we zoom more into here, you'll see that going from Flute to URL, so the distillation that gives the universal feature extractor with a simple adaptation on top, has a massive jump in weak generalization, but not strong generalization. And then adding the residual adapters does the opposite, has the opposite effect. And this is perhaps expected because adding residual adapters means that at adaptation time, you have more capacity to adapt to the particular task, which is important if that task is very different from things you know, strong generalization. And this added capacity is less important for weak generalization. But you know, like I've been talking on and on about all these methods, and remember that strong generalization here is measured on just 5 data sets. So maybe we need to like really, as we are now getting deeper and deeper into developing methods for this challenge, we need to maybe just improve, just have a much larger number of tasks available to really reliably assess strong generalization. And this is one of the reasons that I'm really excited about this new benchmark that combines metadata set with VTAB. So VTAB stands for Visual Task Adaptation Benchmark. It's a benchmark from the transfer learning community where they want to measure transfer learning performance on a wide range of downstream tasks that are natural or specialized, like aerial and medical images, or structured, which are synthetic images, and the tasks usually measure like the comprehension of the structure of a scene. So this is obviously a much larger variety of downstream tasks to study, and the motivation behind this combined benchmark is to allow exchanging insights between the few shots learning community, which was indexing heavily on meta-learning methods, and this transfer learning community, and to improve methods for both. And this led to a very challenging protocol. I'll share some of the conclusions briefly from their initial investigation from Dumoulin et al., which is that the BIT model, BIT stands for Big Transfer. It's a much larger model. So BIT is based on ResNet 101, which is 101 is a larger number than 18, which is what the rest of these use. So it has way more parameters. And it's trained on this JFT data set, which is a much, I think, like on the order of hundreds of million images. So the green line is this big transfer method, which is a large model trained on a lot of data. And the other ones are, the pink is SIR, which is the universal representation method I mentioned, and then prototypical networks in blue, proto-mammal in orange, and the simpler transfer learning in the dark green. So you can see that BIT does very well here. It outperforms previous approaches. But of course, I mentioned this is a larger network and trained on more data. So this is not apples to apples comparisons, right? And you might say, like, I feel like I'm reading some of your minds. You're saying, like, but okay, can't you like scale up the other ones as well accordingly to get more better apples to apples results? I won't go into the details of this, but turns out this is hard for meta-learning models, and friends at University of Cambridge, John Bronskill and colleagues, wrote this nice paper that explains why meta-learning is memory inefficient. I'll just give you the punchline. Remember how you do a meta-learning update. You need to make predictions for the query set, but to do that, you need the task-adapted model, and to get that, you need to ingest the entire support set. So you need the entire support set to get the task-adapted model to make even one prediction on the query set, so to do even one meta update. This is memory inefficient. And here they propose a really nice trick to alleviate this. So in the backward pass, they use only a subset of the support set, but in the forward pass, they still use all of it. And I'm going through this quickly. I'll let you to read their paper for details, but they show that for some meta-learning methods, this gives you an unbiased estimate of the gradient. So their proposed approach here is the black line. It takes the simple synapse model as the meta-learner, and it adds this particular trick to it. And you can see that it outperforms in some particular cases, like in this group of bars, which is from the metadata set, part of the metadata set in VTab, it actually outperforms BIT, that big transfer thing. In other cases, it still lags behind. I'll also say briefly that I don't think scaling up is the only thing we need to do. So the scaled up BIT thing, which are the first 3 bars in every group of bars here, you can see here we're just breaking down the results in terms of particular data sets. There exist some data sets where other methods like cross-transformers or SIR actually work better. So this recipe of just scaling everything up does not, at least in this case, work well across the board. There's some situations where you need to do more than that. And this paper gets into that nicely by, so this paper is studying basically how much can we push simple pipelines. So here they grabbed so-called foundation models, which are large models that are trained with self-supervised learning on some external data set. Here they use the CLIP model, if you've heard of that, contrastive language image pre-training, and they show this is mini ImageNet, so one of the old simple data sets for few-shot learning. They show that you can get this gold star with using this foundation model. And on metadata set, they also did this on the weak generalization tasks. You see you can get a 6% boost compared to URL with the task-specific adapters, the residual adapters. You can get a big boost here by doing some unsupervised learning using this Dino method here. And then, so their pipeline here is pre-training with a self-supervised learning, then meta-learning on metadata set, followed by some simple fine-tuning to solve the task at hand. So it has several stages, and I think more work needs to be done to really pinpoint where this 6 percentage point benefit comes from exactly. But this is just a really nice way to illustrate that we need to be thinking about how to leverage these existing strong models that exist, these models that are already out there, to solve few shots learning. So maybe quickly, how are we doing for time?
We are good. We have 8 more minutes.
Perfect.
Schedule time. Yeah.
Okay, amazing. I don't want to talk the whole time because I would like to take questions as well, but I'll just really quickly go over this next part, which is talking now about how there's this new narrative that few-shot learning might be an emergent property in large models and not something that you have to do something special for in your model to obtain. So over in NLP, I've talked about vision a lot, but there's a lot of excitement now in NLP with models like GPT-3. You can tell these slides are a little bit old. No, there's, GPT-X for X larger than 3. But there's this narrative that these models are capable of few shots learning. But what they mean by few shots learning here is a different type of thing, or a different approach. So this is called in-context learning. And this is very different in the sense that there's no gradient descent, there's no updates to the model to few shots learn the new task. Instead, all that happens is a forward pass. So in particular, I'll show you an example here for a 0 shot versus a few shot task. What happens is that you construct a clever prompt, and then you just feed that into the pre-trained large transformer usually model, and then the output that it gives you is the answer directly. So in particular, to solve a 0 shot task, I don't remember what this example says. Oh yeah, this is a translation from English to French, and you're saying, so you will write as your prompt, translate English to French, : cheese arrow blank. You'll just write this as a sentence that you feed in as input to this model, and the output of the model will be the answer that fills in the blank. So this is 0 shot in the sense that you haven't given it any examples of English to French translation, at least in this phase. Of course, this was trained on the internet, so maybe you can argue there's lots of that. That's a whole discussion. And the few shot version is that you do something similar, but you actually give it some examples. So you would say, translate English to French, and you would say, sea otter, arrow, loutre de mer, or some correct version of someone saying that. And then you would do this for a couple examples, a few shots, and then you would say cheese arrow blank. So that's the few shot version where you give some examples. And then folks have noticed that you can actually create multimodal in context learning versions too, where instead of just giving it just words, you can add images in the mix. And people have developed models that can take such arbitrarily interleaved text image as the prompt. So you would give that image of a dog and say, this is a very cute dog. Then you'd give an image of a cat and say, this is blank. And the model fills it in. So Frozen and Flamingo are 2 different approaches the 2 that I've seen that do this. I'll talk briefly about Flamingo, which is developed by colleagues at DeepMind. And the way that this works is that they basically take snowflakes here means that that module is frozen. So they have a frozen vision encoder that just learns to take images and create vectors for them. They have a frozen language model that has been trained as you train a language model. So these are off the shelf. And then they learn the pink stuff that basically constitutes the architectural glue to make those 2 talk to each other. So specifically, these are initialized in a way. So this part on the right is the text model, and this part is, at initialization, it's the text model. And this part on the left is the vision model. So if you get an interleaved prompt like this, you'll pass the images through the vision side, and you'll pass the text through the text side. So this pink stuff, at initialization, they're initialized in a special way so that they don't have any effect, so that this thing is just the text model. But then, throughout this Flamingo training phase, this part on the right progressively changes from being just text to multimodal image text. And these are essentially doing some cross-attention between visual tokens coming from the vision side and text tokens coming from previous layers of over here. So again, it's an attention mechanism that is, this is all learned end-to-end. The pink stuff is learned end-to-end in this Flamingo training phase. So again, there's more details there that we can talk about later, or you can take a look at their paper. but they have some really impressive results. So they have state-of-the-art results on 6 out of 16 of these particular suite of multimodal few-shot learning tasks. The reason that this is impressive is that some of the other methods before this sort of in-context learning thing actually fine-tune the models for each task at hand. So there's an expensive gradient descent phase there. And here, all you do is this in-context learning. Once you're done training your Flamingo, all you have to do is put together a prompt like that and forward pass it through this thing. There's no gradient descent. So this is quite impressive that it can do better than some of the previous more expensive methods. And they have a lot of kind of fun qualitative results too that I'll refer you to their paper. But you can teach, for example, a model to do arithmetic from handwritten notes. You can say, you can give it this picture of 5 plus 6 and say, you know, that's 11. And you give it a few examples of that, and then given new pictures like this one here, 3 times 6 with a blank, it will tell you that that's 18, which is kind of fun. Now, there's a lot of discussion in terms of like, what is going on here, right? Like, this is very impressive and it's very exciting, but we lag behind in terms of understanding in-context learning. And there's a lot of papers on this topic, actually, that I won't have time to talk about today, but I'm happy to discuss more. This paper from Reynolds et al. Tackles the question, is this really few-shot learning, or is it more like locating, using the few examples to locate one of the millions of tasks that it saw previously? Because these models are trained on the internet. They know, they've seen a lot of things. The internet is very, very large. So is this learning de novo, or is it more like retrieving some knowledge that you had obtained previously? And here they argue for the latter. And their argument roughly goes as follows. A learning algorithm has the property that the more examples you give it, the more training data you give it, the more it improves. But for this in-context learning stuff, we actually notice that the performance saturates quite quickly as you give it more examples. So you can see from here, for instance, this is like the number of shots, which are in this case, like the correct demonstrations for how to do the task. As you give more and more of them, the performance saturates. And here in particular, they make the argument that you can actually push zero-shot performance really high if you just get creative with how you construct the prompt, how you prompt the model to give the answer. And if zero-shot can work as well as few-shot, then maybe the reason it's working is not that it's leveraging those few shots to do learning, because even without those shots, it does quite well. So here they create this master translator prompt format. So to prompt a language model to do translation, you would say, a French phrase is provided, colon, source phrase. The masterful French translator flawlessly translates this phrase in English, colon, blank. And saying it this way gives better results than just saying, you know, something simple like, please translate this sentence from French to English. So the fact that you can do such manipulations to the prompt and push zero-shot performance is maybe some indication that this is doing retrieval rather than learning. And then there was this interesting paper as well that came out that showed they compared in-context learning with either zero demonstrations, so zero shot, or few shots, so with demonstrations, either with gold labels in this gold color or with random labels in red. And you can see that gold and red are not that different, which shows that if it's doing some learning, what it's learning is probably not a mapping from inputs to outputs. You can still argue that maybe other things are getting learned, and in fact, they do argue that in that paper. To sum up, there's a lot still to be understood about why this is working. So I've reached the end of the talk. Maybe I'll very briefly summarize in -1 minute. Things have changed a lot recently in terms of benchmarks, models, and the role of meta-learning has transformed massively. I think that the evaluation protocol and benchmarks that we use really influence the conclusions that we draw and consequently the models that we develop as a community. So I talked about small convnets biasing us towards meta-learning approaches because transfer learning doesn't work very well at that scale. Homogeneous benchmarks might have biased us towards feature reuse. Metadata set came along, which was a step in the right direction in my not so objective opinion, perhaps, but metadata set probably biased us towards weak generalization because we only had 2 held out data sets initially. And so now there's metadata sets in VTAB, which is a much stronger benchmark, and there's these multimodal benchmarks as well. But it's important to take a step back and notice what other biases do we have in our protocols and our benchmarks, and how is this biasing us in terms of what we develop as a community. There's 2 ongoing work pieces that I'm doing, but I'll tell you about that later if you're interested, and I'll stop here and take questions.
Let's thank Eleni for